So let's start. We are already a bit late. This is a continuation of the previous talk where James introduces the modeling of cell shapes. The first plugin that takes that task into account is the contact energy. But I will present you here with three others plugins. But just to be uh, sure, let's say what I'm going to cover in this lecture. A small motivation about cell shapes that James has introduced already in the previous one, and then I'm going to go step by step in exercise where we will analyze the three plugins that I have told you before. Let's go and then here, cell shapes. James showed this picture, this slide before about the big variability of cell shapes we have in nature. Even cells which crawl alone, like the mesenchymal cells, different kind of specific types of cell, like nerve cells and sperm cells. We have also this kind of cells that are epithelial cells, very common in animal. And James has shown how to go from one type of cell to another type of cell with the transition, epithelial mesenchymal transition, adjusting the contact energies. But now, in general, at this stage, we are dealing with mesenchymal shape of cell shapes. We are analyzing isolated cells, let's say, for now. Okay. Let's see. There. CompCell has a structure that work with plugins and steppables. I think somebody has told you that already, but I don't remember who. And we are going to create a basic simulation. That simulation will include the plugins we want to analyze in this lecture. And these plugins are the volume constant plugin, the volume flex plugin, the surface plugin, and the length plugin. Each one will attack, let's say, one characteristic of a cell, as the proper name is telling that. It's volume, the shape of the surface, and if the cell is like a line cell, a stretched cell, or a compact cell, a round cell. Everything I'm gonna do here in the widget is in the demo materials with the names that will appear in the slides. We can follow doing the same as I am doing here in the screen, but you don't need that. If you want to, you can load download the codes from the students' materials and analyze them when they load it into edits. Okay, I think we doing that here. I will follow here to make this example. Let's create a basic simulation. You have it doing that in the previous lectures today and yesterday, I think. We start with this new simulation here, new CCD project. I'm going to give you a name which is similar to the previous exercise that James gave to you. I will call this module two, two under two cell shape. Okay, then I will advance. And here we have this let's see dimensions. We're gonna choose 100 to not waste much time to run the simulation. And we are going to start with the rectangular slab. Go ahead, then we add our only one type of cell here. I want to call test cell, add, and click next. No diffusion fields for now. Next. And here is the point where we included the plugins you want. As usual, contact is the first one you always must have in the simulation. But now we are going to add volume flex, surface flex, and length constraint. And we'll get rid of cell neighbors. We don't need that for now. The cell center of mass is always there. Keep it. Advance. So the simulation is finished. And now we are going to see, this is the summary of the basics template to create the simulation. And here, when you finish the simulation, again, you have the project name at the left panel of the two edits. You double click it, and you open the three files that the simulation contains. The first one is this Python. Python is main Python file, which has just the registration of the simulation for now. Here we are going to include something else if you need to include as external steppables that I will explain later today. The second one is the XML file, which is, where is that? I have both here. I think I'm going to stretch a little bit here. The XML file we create basically the simulation with some basic essential parts like POTS tag and all the all the plugins you want to load, you have loaded in the wizard. They appears here. See, here are the cell type, which is included by default in the simulation. POTS and cell type are included by default in any simulation. Okay, but the ones we have included now are the volume, the surface, center of mass is there, contact also we include, and the last one here, the length constraint, and the uniform initializer, which was included in the wizard. Okay. The third one is the third file is the steppable one. The steppable one is a file where you write your own instructions and functions and measurements and the plotting and saving data. It's everything else is written here by hand by you. Okay, but we are not using this very much in this lecture. Just the next one. Going ahead. Let's see. So after you have the simulation built, you come here as The other time, open the player. It takes a little. This is what you have. Just a bunch of cells in a in a in a in a square 100 by 100 grid. Okay, so let's continue here. Uh, I think I can skip this one because we already know how to do that. The player opens even uh, when you have the player, you have these four buttons here. These four buttons control the execution of the simulation. You can stop, you can step it, you can pause, you can run. If you run, pause, step by step, one by one, and end the simulation. Okay. So this basic simulation is this in this file in the student's material. Okay, E221A zip. Now let's modify this file. Let's go to the XML file, and which is here, which is here. In the XML file, we are going to change the beginning of the simulation, the size of the simulation. It's here. We have here, initially we have this dimension. The grid is written from the coordinates to 20 to 20 to 80 in both directions. Okay. And we want to change this to decrease this domain to 40 in both axes to 60. Okay, in doing that, the green line you have before is shrinked to this smaller one in the middle of the previous one. So our domain here is a domain of 20 by 20 pixels or voxels. Okay, and if you run the simulation now, where is my? Let's save it. Oh, here, yes. You immediately have the sizes decreased, okay, and the simulation rules. Let's put this here. Now we can change the aspect of the cells to have only one cell in our simulation. How we do that? We change the width of the cell from 7 to 20. Since the grid, the domain has only 20 by 20, we have room to create only one cell, which will fit all the domain. Okay. We have to save it and go back to the simulation and again. There it is, our cell. Only one cell, one in the domain, the big domain, which is 100 by 100. The grid, the LEDs. Okay, so we know how to change the size of the initial cell. Let's continue and move to the following step. This is the summary of this what we have done now. And this small exercise is also in the student's material with the within the file 221B. Let's go ahead. Now, this is what we have seen in that simulation. Let me start over to show and go the simulation step by step here. See, it starts a big one, like the first image you have in the slide here. If you advance, the cells start to shrink till some volume which is compatible with its target volume, which has been defined by default. When you load that volume plugin, it loads with you some size for the, I'm going to show here, this line here, volume. Okay. Let me go ahead aqui. Well, I don't know why it's... I know. Tá. When you calculate this, when you include the plugin has some default data. These default data are there. See, lambda volume and target volume. But how does it work, a plugin like that? Those plugins, like the energy one, not like the energy one, they works including a energy term in the Hamiltonian of the system, which is inside the CompCell machine, let's say that. And this energy times works in this way. We have a lambda value here, which is the intensity of the energy term, and the difference between target value, which is the volume where want the cell have, and the cell volume that is the real volume of the cell at some Monte Carlo step. Okay. You understand that? I mean, because of this is a stochastic process, the cell volume oscillates around the target one. But how big are these, or how intense are those oscillations is mediated by this lambda value in front of the steps. And look also that this difference is squared. So it's like a string, you know, energy of a string. If it doesn't matter if you have a small volume or a big volume compared with target volume, the difference is always square, hence the difference is positive. Okay? Here you can understand that. See, here's we have in this curve here, the V target. And we have the volume in the horizontal axis. So if the volume goes to the increases is bigger than the target volume targets, the energy is positive to the right. But if the volume is smaller than the volume target, the energy has the same amount, positive amount. So the minimization of energy brings the energy to the volume target, which is the bottom of this parabola here. And the lambda volume is the coefficient of this parabola. So is how much is this parabola is open or more stretch, more close. Remember from the classes of mathematics you have long time ago? If the lambda value is negative, this parabola would be upside down. Lambda positive is upside up. Okay, and the three plugins work in the same way. It's they have a target parameter and the real um, characteristic of the cell at some point of the simulation, at some Monte Carlo step. And the cell calculates this difference here from the target and the real value to see if the evolution of the system, if the energy goes to a minimization according with some probability function, which I think James has shown yesterday. Okay, let's see how we play with the volume constant. Okay, first, let's put lambda volume here for the other plugins to 0. Doing that, we are going to eliminate the function of the surface and length constraints in this simulation. So what we have to do is to come here and put 0 here in the surface plugin, line 31 here. I don't know why mine is 32 now. Anyway, so doing that, we turn off this plugin. Okay, and we do the same in the length constraint. Here, we put 0. So we are turning off both surface and length constraint plugins. Okay, now we save the simulation here, and we are going to play the simulation. Let me get the player. We start at the same time. And now we have something else, something different. See, it's more rounded than before. And because there is no competition between energy terms in volume and length constraint and surface volume, because we turn them off. It's only the contact energy and volume playing during the simulation. Energy terms playing in the simulation. Okay. Continuing here. Now, how do we see the influence of this plugin? How do we manage this plugin? This is the summary of the simulation. Here what we saw. And see, this is the difference between when we have every plugin turned on and now you have only this one. This is exercise 222 in the students' materials. Okay? Now, let us do the following now. Why do the cell shrinks at the beginning? Because, see, we have, when I told you, when we load the plugin volume, it came with some parameters defined. And it has at the beginning, for definition, a target volume of 50. But when we created the cell, we imposed that the cell should have 20 by 20. That means 400 pixels. 400 pixels. Okay? So we want to keep that size. We're going to change this 50 value here for the lambda volume from 50 to 400. And we're going to save the simulation. And now, this is what we should see. Again, stop, step by step, start. I'm playing step by step, see? And I'm going to release the simulation. The cell doesn't shrink anymore because its target now is 400, not 50 as before. Okay, continue, Iris. Now we can try to make the cell bigger by changing this value. For example, we can choose to put here 1,000 as the value. Oh, save it. Stop. So the cell starts with 400 pixels at the beginning because we created the cell with 20 by 20, but we imposed that the cell must grow to 1,000. So the cell grows. Again, now it's in a quick way. It's very quick, the cell goes to the target value and oscillates around 1,000 pixels. If I put here the cell, the target volume to 0, and let's see if I can do that here. I don't think I can here. Here, for example. As James just told you at the previous lecture, you can change parameters here on the fly. Just type the same kind of quantity you have. For example, if it's an integer, should be an integer. It's a float, it must be a float. See, immediately the cell shrinks. If I go to 0, the cell disappears. So put cell target to 0 is a good way to kill a cell in CompuCell 3D. It's very efficient. When you can put the volume target going to 0 slowly if you want to, but that must be done in the steppable, not here. Okay? If you have, I should mention that. Let's go back to the simulation. If you put volume targets like, let's start with 1,000, and then I will put here 20. The cell also disappears. Okay, this is a problem. This has to do with the balance of energies, with the contact energy and the energy between different types in the comp cell. The contact energy plugin actually. We have to handle that to avoid this kind of problem. Okay? Well, going ahead. We did that already. Here's what we see. So, explain what happens with this. Now we are going to change the lambda horn. We have played with target horn. Now we have to play with the lambda horn. Let's change it to from 2. We should do that to, oh, let's to have the code. We are going to change the lambda volume to 100, to 2 to 100. That's what happened in the function energy, plugin energy. The blue line is the old one. When you have a small coefficient for your parabola here, if the parabola is the coefficient, the lambda is big, the parabola is more closed. So you are going to turn your cell a little bit rigid during the simulation because you have a very strong constraint. I mean, you are saying to the cell doesn't change its shape too much. Okay, so the fluctuations will be reduced. Let's go to the code and save it. See, I'm saving, I am changing always the same exercise, but in the students' materials, you have exactly one file for each one of those exercises that are named here 222, 223, and so on. Okay, so this one now have oops, I have to stop and begin it. See, now we have here the plugin with lambda volume 100. It's a float term, note. It's at a point here. When you put it to run, see, the cell is rigid. Cannot adjust its shape anymore because you are saying to the cell doesn't change too much, increasing lambda. The volume is frozen, basically. Right? If you decrease a little bit here, 50, for example, it starts to fluctuate more until to compare the old value to much more. So what happens? Remember, the calculations are stochastics and according with the Boltzmann probability. So looking at this, what happens when we change the fluctuation, we didn't have changed what James don't like to call the temperature of the system. It's a membrane fluctuation amplitude, T, in the POTS part of the XML file. And then, since we don't have changed this denominator in the exponent of the probability function, if you increase delta H, what happens? Oops, sorry, I have to go back. You increase the rejection of the accepted probability because since we increase the numerator here of the fraction, the fraction will be bigger and 1 over E will be smaller. And the probability to accept the, 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 the change, the flip change, is much smaller. Have you understand that? Did you understand? I hope so. Let's see. So if you want to uh, increase to keep things more or less constant, if you change the lambda volume, if to increase the lambda volume to 100 here, back to 100, okay, we have to change the temperature as well. And this is, well, let's do in the file here. We have to change this value here to 102. Okay? So go back. And then you have more fluctuation of the cell membrane, even with this lambda volume bigger. See here, 100, 100. But it's a little bit different that we have before. See, if I put here, I will change here to, let's see if I have here. See, this is what we have before. I can change here to show you. Let's go back to 100 to 10 here on the fly, and to 10 here on the fly. See? You have those situations shown in this slide. Oh, here is lambda value is 100. Okay, let's put lambda value 100 here. The cell is frozen, doesn't move. But if you have here the 10, you have the cell evolving, but much more smooth. In a way, much more, the cell membrane is much more smooth than it is when we have 100 with 100. Okay? And why does it happen? Again, nah, the slides are showing what I have done already. When we increase both values, we effectively decrease the relative effect of this calculation against the contact energy between cell and medium. Because the total energy that enters in the energy that enters in the probability function delta H that it was in that here is the sum of all energies in your simulation, contact energy and volume energy. Okay, so since we don't have change anything in the contact energy and only change in the volume energy, so we changed the relative contribution of the contact energy in that calculation. So we can decrease one of those here to get something more smooth. Oh, I don't know. Oh, something was wrong. Sorry. Contact energy as well does. Yeah. Of course, you have seen that with James like the previous one. But let's go ahead. Now, how temperature we are going to analyze how temperature versus constraints. We can, during the simulation, go to temperature equals to 1 here. Of course, the cells is frozen. Why does that happen? You have T1, T10, T100 during the set. 1, 10 is still frozen, and moving. Okay? That's what happens in the probability calculations. T1, T10, T100. So increasing the temperature, you increase the rejection of accepted flips. So that's what will happen. So if you have t equals to 1 here, you only have accepted flips if delta H is smaller than 1, is smaller than 0 here. The energy decrease. If not, you don't have anything accept. Okay? But if you increase both, then you can have acceptance of flips here because you decrease the ratio delta H over T. If the ratio delta H over T is small, you have the blue line here. So you reject most of the attempts of flip. Okay? Okay, let's go now to the surface constraint. I think James has shown something like that in his presentation today. It is the how a surface of a cell is calculated. For example, here we have this volume of 1 pixel only, and the surface of this pixel is 4 because it has 4 contacts with the exterior world. Here, 2 by 2, we have 8, and here is 21 with 20. And the number of surfaces, the amount of surface is take into account the interface between the cell and something else. Okay, is the black line here is counts as 1. And here this corner counts as 2, 20, 19, and 20, and so on. The energy term is similar to the volume term. We have the intensity, the lambda surface, the target surface, and the actual cell surface. And if you are dealing in a 2D square lattice, we can say that to start, the relationship between surface and volume is 4 times the square root of volume. It's like actually, in 2D, surface is like perimeter. Surface is really surface in a 3D simulation. Okay, here we are dealing with the surface program as it is measuring the perimeter of the cell. Because this. And of course, and the volume is the surface. I think you got that. Since we are dealing in 2D, we don't have volume. We have only surface. And we have a perimeter for the cell. When we count here 1, 2, 3, to 8, it's the sum of the is the perimeter of the cell. So if you have um, a volume which is a surface of 1 pixel here, 1 voxel, okay, the perimeter is 1, 2, 3, 4. And the square root of the surface is 1, the square root of 1 is 1, times 4 is 4 sides, four contacts between the cell and the external world. If I had a 3D, things are going to be different. I would have a surface which will englobe the cell. Like yesterday when I showed that 3D foam, remember? The 3D foam has I showed two images. One was a cutting, a 2D cut from the system, and another image with the 3D version of view of the foam. There I have volume and I have surface, real volume and surface in 3D. Okay, let's go. Exercise 2.4. Now we are going to recall the old values for the first basic simulation. Here I have 10. Lambda volume is 10. The target I'm going to let 1,000. Medium test 0, I think. No. Let's turn off the medium test, medium cell. This one, 0. And now, since our surface, which we are calling volume, has 1,000, our surface, actually our perimeter, is 4 times the square root of 1,000, which means about 126. Let's put this value here in the surface plugin. Lambda surface goes back to 10. And target surface is 126. Let's keep the constraint length still off. Okay, this is exercise 224 in the student's material. Let's save it. And no. Okay. Now there is competition between volume plugin and surface plugin, because volume plugin wants to keep the 1,000 pixels in the cell, and the surface plugin wants to keep the target surface as 126. But 126 is a shape of a square. And then the cell doesn't round up because of this competition. See? This is what we have. The comp cell is trying to match both at the same time, volume of 100, 1,000, and the surface as 126. The cell is going to be that way forever. Okay, let's change that. Let's try another values here. We can do that on the five, no? For example, if I decrease, where is this? To 60, the cell doesn't move. Of course, it cannot change because I'm trying to impose a target surface that doesn't comport the size of the cell. So nothing change. This is the minimum that the cell can have is this shape here, this square. Okay? If I increase a little bit for this value 125, the cell starts to be more flexible. The membrane starts to round. More, 300. The cells starts to fall apart because he wants to, to achieve that 100 surface as a target. So some pixel of the cells start to separate to because isolated pixel has four units of surface. Okay? It's detached from the whole thing. And 600, even so, even more dismembered in the cell. Exaggerated situation is the last one when we disassembling of everything. James did that in the previous lecture by changing the contact energy, remember? Let's go back to 200 here. Let's see what happens. He told you about that also. If you change back the values to the original values, since the pixels are separated, they may not find each other, and we have blocks unfrozen. Okay. So let's go. Now we can go to the of course we can play a little bit there with the lambda surface as well here, but the effect will see similar to what we have done with the playing with the lambda volume parameter. Okay. The last one then is the length constraint. Again, the same shape as mathematical form as the other ones. Intensity, the lambda constraint, and a target length, and the real length, actual length, actually. Okay? And let's edit again our simulation here. Go T10, lambda volume 10. Let's put lambda surface 0 now to analyze only the competition between surface and volume. Surface, no, length and volume. And here, go back to 10. That's it. Yeah, save it. Now we have to choose some parameters to set the parameters for the plugin, the length plugin here. he has a lambda surface which was 0 because we have put there before, 5. And again, let's say that we are approaching the length of the cell as the square root of the volume. What does that mean? We have a square. If you have a square here, then the length is the length of a side of that square. Okay, so our volume is 1,000. A square root of 1,000 means a square of side 32. So this is what we have to write here. And save. Again, exercise 225. Let's start this one. Let's see if everything is okay here. Then, yeah, I think that. See, nothing has changed, even with this uh, constraint turned on, because we are imposing that the length of the cell must be the length of the square where the cell was created. Remember, the cell was created as a square of 20 by 20, and then grew to 1,000, and we have taken the square root of 1,000, which is 32. So the cell is still rounded. But we can change this. This is what we have seen. And now let's change the length. Contact length here. No, sorry, length constant. Here. We're going to change this number to 40. The cells start to stretch in one direction. Here. Let's go further. 60. See, the cells assume a bastonet kind of shape. And if with a bigger one, the cell stretches. I mean, so now uh, we are saying that the length of the cells can be bigger than the square where the cell was created, the 32 size. So then you can play with the size. I don't know if you can go further. 100 is, I think, is too big. The cell can be be torn apart. Okay, so let's change a little bit. The power value is lower than 32. For smaller than 22 is smaller than 25. Nothing happens. Because again, this length cannot afford to have 1,000 volume cell inside. So the minimum is 32. Okay? If put 10 here, like the image there in the slide, it doesn't move, but now we can change the lambda. We want to force this. Oh, the cell freezes. Should not freeze. Let's put a little bit. Nothing happens because the strength of this interaction is too high and the cell cannot move. I think I have chosen a small. Yeah, the cell freezes, yes, it's okay. It's correct. This happens because we have changed the shape of the energy term. Remember? Well, let me show you back in this thing here. I think this value here. Increasing the lambda, we close the parabola. That means we have more rejection for the accepted flips. Okay? Well, that means we are increasing this delta H because lambda is bigger. And if you increase delta H, you reject more acceptance of flips. Okay? So I think it's that for today. If you have some questions, we can do now. Thank you.
Yeah, I had a question.
Okay.
So when you calculate the perimeter, it looks like if your boundary is at a 45-degree angle from the coordinate axis, it will be square root of 2 times 2 large. And then like I
Well,
remember when you set the preferred perimeter to 60,
yes.
with the volume of 400, um,
Yeah.
to me, I think that should become a circle, but then if you have a
No, the
circle and
volume
you
was
compute,
1,000. I think the
okay, well
volume
then
was.
even more so, the surface, the perimeter should be minimized by a circle, right? But if you're calculating it using the horizontal and vertical steps, then actually a square has smaller perimeter than a circle of the same area.
Let me see. Where is that here in the presentation? Well, here. This one?
Yeah. Because if you try to set the preferred perimeter to a value lower than is allowed by the isoperimetric inequality, then you should get a circle because
But
it should try to minimize
the circle will not englobe all the cell, I think. The 1,000. There is a competition between both. The exchange of the energy change doesn't allow you to move the boundaries here because the target is very small.
Yeah, so if the target is too small, then it should become a circle, right?
Not on a lattice, as you pointed out.
So that's the reason. It's because the way the perimeter is computed using the horizontal and vertical lines.
That's right.
Yeah,
Oh, okay.
yeah. We
Okay,
don't
thanks.
we cannot calculate the angles here, no?
You can do a perimeter calculation using longer radius, and in that case, it smooths it out. But if you use nearest neighbor calculation for the perimeter, then you get a square.
Oh, yeah.
Okay. Okay. Is there a way to fix this problem though?
Yes, if you use a longer interaction range for the perimeter calculation. And you can set that. That's an option in Composite.
Oh,
Or
okay.
maybe using
Okay.
hexagonal LEDs as well, doesn't James?
Yeah, you could just switch to hexagonal lattice and run the same simulation, show them what it looks like.
All right, thanks.
Why don't you do that, Gilberto? That would be quick. Just change the lattice to hex lattice.
Let's see. That I have to use those values here. T equals to 10, no surface constraint. Zero here. And here. I don't remember the syntax
Would
for.
you explain code snippets to people? Because that's not a concept people have. So
Oh,
Twittig has very powerful help in editing simulations.
but I don't remember, Jim, how to include the syntax
Yeah.
for
It's
hexagon.
in the pots. It's in the pots block.
Yes, I know, but what's the syntax?
Just
Is latency?
never mind. Don't worry, Gilberto. We can show them another time.
Okay. Yeah,
Oh,
sorry,
or
I don't remember
why
the
don't you
syntax for
go to the
it.
go to the code snippets, ask for a new pots block, and it'll give you
Ah,
the option of setting it. If it doesn't do that, you can look in the manual. Show them where to find it in the manual.
I think it is easier then.
No, just hit code configuration. Hit CPM configuration. Okay, comment out now. Okay, that's fine.
100 no further square here. Here we can choose another kind of grid, which is a hexagonal one. Okay. And this is not with right angles
Yeah.
as before. And click OK. So when we do that, we replace that old pots environment here with this new one, which has this. What is it?
Why don't you make it bigger so people can see? Full screen, and use a bigger font. There you go.
I think it didn't enter here. CML pots configuration. Replace. Hexagonal. Okay. Ah, now it is. See? This this line here is a new one.
So why don't you explain to people what you're doing with code snippets?
Okay. As James said, to edit it comes with some powerful tools to change your simulations during your project, for example. Okay. So if you we have here two basically tabs. CC3D ML, which works with the XML file, and the CC3D Python that works with steppable Python files and Python files, main Python files and steppable files, which are written in Python. And the good thing of this, those blocks are how do you say, pre-mounted here, pre-built here in the tabs. For example, if you, let's say here, I wanted to include, I want to change this a little bit, another plugin like boundary pixel tracker. Okay, when I click there, I have this new block here, which loads the plugin automatically, and it says what neighbor order should be calculated or found, the pixels which make boundary with another thing in the simulation. For example, in that simulation I was running, let me see here, I could use this plugin to calculate, if I had another type of cell here, I could calculate how much pixels of these cells is in contact with anything else in the simulation, because he only keep track of the boundary pixels of the cell you are dealing with. Okay, there is another one here, which neighbor tracker. This is a very good one, which tells you, keep track of, if you have a bunch of, again, let's talk my foam simulation from yesterday. We have that foam, lots of bubbles. This plugin neighbor tracker can tell you at any Monte Carlo, at any time of the simulation, any step of the simulation, who is neighbor of who. Okay, for example, in that simulation, I had at some point 30,000 bubbles. Using this plugin, I can say who is the neighbor of who for any one of the 30,000 bubbles there. So this is a kind of measure of neighborhood measurements for the simulation. If you have cells, you can tell whose cells is neighbor of which one. And this comes then as a pre-built blocks in the editor to edit. The same serves as the Python module, the Python tab, but that will work with the steppable. Okay, so in the steppable, which is this has this structure. In this file, should I go on, James, explain the steppable? Do we have time? Well, that's a little bit. It has predefined functions, and you can introduce more functions as you need to execute your simulation. And if you need something that is pre-built, for example, a loop like that here in Python for cell in self-cell list, print cell ID. This block comes inside this default steppable, but we can put something else here, like in this visit here, visit cells of a given time. For example, in this loop, I will say that the loop should be done over a specific type of the cell type. So I type here, for example, in that simulation I am doing, test cell. So if I have multiple types of cell in my simulation, when I do a loop like that, I will loop only of the type test cell, not in the other ones. So you can see there are lots of pre-built snippets here that even inside each sub-tab here, you have a bunch of tabs, graphs, mitosis, lots of things that I will teach you later this day. The growth steppable so. Okay. I don't need that. So here, neighbor tracker, I will get rid of this. Pixel tracker. Come back. The only thing I have changed here is the hexagonal grid. So it looks like the same here. See, now the hexagonal grid, the cell still moves, and you can barely see here hexagonal behavior in the shape of the cell. 1, 2, 3, 4, 5, 6 sides. The grid here is hexagonal, not square like it was before. At the square grid, the cell was a square, remember? Here, in the smallest one, here. Now, in the hexagonal, the smallest cell is a hexagonal. That's okay? So it adapts to the grid, let's say. Any question more? Okay, then thank you again. See you later today.